Yo, what's going on, man? What's happening? So today I want to talk about dependent voltage sources. As you can see here, you have a voltage source here, but we also have like an extra wire protruding out of it, right? And all that means is whatever this voltage on this wire right here, whatever this voltage is, or the voltage difference across this resistor, right, is going to be used to be multiplied by 4, right? Multiplied by 4 to create the voltage here, right? So whatever the voltage difference is on this resistor is going to be multiplied by 4 to make the voltage for this voltage source, right? And when we say multiply by 4, we basically just mean like it has a gain of 4, right? So like I want you guys to remember that. So again, just repeat it one more time. The voltage difference across this resistor is what's going to dictate the voltage that this voltage source produces, and this voltage source has a gain of 4, so therefore we're going to multiply this voltage difference by 4, right? So I want to also show you one more thing before we could get into solving this problem. As you can see right here, right? Oops, I actually messed that up. So let me move that real quick. You're gonna have Vx, right? So right, so we got the voltage difference across Vx, right? As you can see, this is the high potential side, it's the low potential side, and as we know, voltage difference is high potential. Voltage difference equals high potential minus low potential, right? So we're gonna find the voltage difference across this, and we're gonna multiply that by 4, as you can see right here, and that's gonna give us the voltage of this voltage source. This is what this is gonna look like for like a basic electrical plans or whatever you call that crap. That's what it's gonna look like for like a drawing, right? A diagram, an electrical diagram. This is what it's gonna look like mainly. But in LT Spice, this is what LT Spice has to look like. So again, we have our, as you can see, this is our wire. This has its high potential. Our high potential is here. Our low potential is here. We would do our equation. Voltage difference equals high potential minus low potential, and we would find the voltage across the voltage difference across this resistor, and we would multiply it by a gain of 4 right here, and we would have our voltage on the source. So now we can get into solving this problem. So let's do that now. And oh, I was doing something earlier, so let's go ahead and get rid of that. All right. Well, first thing I want to do is I want to label our known points, right? So we know our essential node. We're going to label that as VA, right? So our essential node is VA. We're also going to label ground, and ground is theoretically always 0 volts. So let's go ahead and label that. Okay. And is there any other points we can label? Are there any other points we can label? Well, we can't label this, right? Because you would, since it's the negative terminal, you would think it's 0 volts, but obviously it's not 0 volts, right? Because you got the negative terminal coming out here, right? And it's going into 0 volts, right? It's gonna go through a resistor, and as we know, when electricity goes through a resistance, right, Ohm's law is going to take effect, right? V equals I times R. That's going to take effect here. So that means there's going to be a voltage. There's a voltage difference across this resistor, right? And we know low potential travels to high potential, right? So if that's the case, that means this has to be negative. If this is 0, then this has to be negative, right? Because there's no positive number that's lower than 0, right? So this means this size has to be negative, right? And we don't know what that negative number is, so therefore we don't know that. And since we don't know this, that means we can't know this, right? Because if we don't know this, then how can we get, like, the voltage difference of 60 that we need here, right? So yeah, exactly. So we don't know what's here, and the same applies here because the same thing with the resistors. So now that we labeled all the points that we know, let's go ahead and solve the problem. So we're gonna solve for VA. So let's do that. So we're gonna have VA minus 60, the voltage difference of this wire, right? So because we're doing the first wire right now, right? If you guys remember our rule for this, so we're gonna do the first wire. So VA minus 60, right? Divided by the total resistance, right? Total resistance, because this whole wire is a series circuit, right? And we're trying to find the current across this wire, right? This whole entire wire is a series circuit, and we're trying to find the current across this wire. So we're going to have to use our series circuit rules, and we're going to have to divide this by the total resistance to get the whole current that's traveling through this wire. So let's do that. We're gonna have 35, right? And we're going to add that into the voltage difference across this, which is going to be V minus 0, right? That's the voltage difference across this resistor. And we're going to divide that by 5, right? To get the current on this wire right here. So we found the current for this wire, and we also found the current for this wire. So now we're going to find the current over here. So let's do that real quick. All right. Just going to, where's a better place I can put it? I can put it right here so you can see everything. All right. So let's see. So we know this is equal to 4 times VA, right? And we know VA is equal to well, it's going to be, well, my bad. It's going to be 4 times the voltage difference across this resistor. And what's the voltage difference across this resistor? The voltage difference across this resistor is VA minus 0, right? Because as you can see, this right here, VA minus 0 divided by 5, that is the current across this resistor, right? We don't want the current across, because remember, this is a voltage-dependent voltage source, right? This is a voltage-dependent voltage source, right? So we want to find the voltage here. And obviously, the voltage here, you know, high potential, low potential, the voltage difference across this resistor is going to be VA minus 0. So let's write that down. We're going to have VA minus 0. Well, first we're going to do 4 times VA minus 0. And there we go. We wrote our first equation. So let us do that. That way we can do that. All right. Let me see what I'm looking like on time here. Okay, we got plenty of time actually. Holy crap. All right, so let's see what we can do here. We got so let's start simplifying now. So we can do, well, first we're going to define the least common multiple of oops, actually I messed up here, right? I actually messed up here because sadly we cannot do all of this in one take. I wish we could have. All right, so we're gonna have to find the current across this wire, right? So yeah, I messed up there. Let's do VA minus 4 times VA over 0, right? We're gonna do that, and we're gonna divide that by the total resistance, which is gonna be 50, right? Sorry guys, I did not mean to mess that up. Silly me. All right. So now we have our full equation, and now we can simplify. So let's do that. All right. So we're gonna have, what do we have? We have VA divided by 35, VA divided by 5, and VA divided by 50. And we got to add that all together. So actually, we even have a VA here. Oh, that's gonna suck. We gotta fucking deal with that VA. All right, let's do that. So we got 4 over VA. So we got 2 VAs here. We got 50 and a 50. I guess, yeah, so never mind. So it doesn't even matter. All right, so we can find the so let's see. So we're gonna have 35. So what can go into all of those numbers? 5, right? So we'll have 5. If I can write that right. We're gonna have 5. So we're gonna have 5 can go into 35 7 times. 5 can go into 5 1 time. So we're just gonna have 5 there. I think that's how that works. And we can 5 can go into 50 10 times. All right. So we're gonna have to go down again, and we're gonna have 5. So what are we gonna do? Yeah, 5. Yeah. So 5 can go into 5. 5 can go into 7 no time. So we're just gonna write 7. So 7, and then 5 can go to 5 1 time. So we're just gonna write 5, and then 5 can go into 10 2 times. So we're gonna have 7. So we're gonna have 5. Hold on. So we're gonna have 5 squared times 7 times 2. So that's what's gonna, yeah. So it's gonna be 350. They can all go into 350. So 350 can go into 35 10 times. So let's write that down. VA 10. And 350 can go into 570 times, so we're gonna have 80. All right, and then VA can go. 50 can go into 35 7 times, so we're gonna have 87. And then we're gonna subtract that from so we gotta multiply 7 times 4. So we're gonna subtract that from 28. And what is 87 minus 28? 7 minus 28. That is equal to 60. So we're gonna have 60 over 350, right? So we're gonna have 6 over 35. I don't think 3 can go into 35. Can 3 go into 35? I don't think it can. I don't think it can. Yep, it cannot. All right, so we're gonna have 6 over 35. So we have 6 over 35 VA, and that is gonna be equal to. Hold on, let me see how much time I have left. Okay, we're still good. All right, 35 VA, and what are we gonna do next? That's just gonna be 0. All right. What else we got? I think So the only thing we got left is just the 60. And 60 over 35, they both can go in the 5, so we're going to have 12 over 7. Negative 12 over, positive 12 because we're bringing it over, right? So 12 over 7. So that means we're going to multiply 35. 35 times what? 35 times 12? Yeah, 35 times 12, that's 420. And 42. So 420 over 42, what is that? 420 over 42 is 10. So VA should equal 10 according to our calculations. VA should equal 10. VA equals 10. Let's say positive 10 volts. All right. So let's see if we did our math correctly. Let me get rid of that. All right. Did we do our math correctly? Okay. We did it a little bit correctly. We're just a tad bit off. One went wrong there. But we got somewhat of the right answer. So there you go.